Alright, hell yeah. So one of the commenters wants me to go over trigonometry and linear motion and also how this applies to waves. And so here's a pretty cool example that I've always thought about, which is sinusoidal motion, also the motion of a circle, and also the motion of a wave, and also linear motion. So we have a car. And so this scenario is going to be like, hey, you're just on those side streets and every intersection has a stop sign. And the other block is not too far away, and so you have to go from 0 speed up to hella and then all the way back to 0. And then you just have to do that process over and over again. So this is the same thing with uncontrolled intersections, but the worst is when you have like stop signs every block that you're doing this, starting 0, getting up to speed. And so we're just going to say, I'm just going to do everything in meters per second. So the top speed here is going to be 15 meters per second. So we're going to be going over the speed limit, in a 25 mile an hour zone. This is about over 30 miles an hour. And then we have a speed here of 0 meters per second, 0 meters per second. Now the first question that I had is like, well, what's my average speed going to be? And I'm going to Google at least kind of what the distance of a city block is. Alright, hell yeah. So I just Googled this, and just in my town we have these just everyone has just really short blocks now. There's probably not stop signs between each of these, but you get the idea. So it would be 58 meters. So this whole distance is going to be a distance of 58 meters. Now I think we have to do kind of like what comes first, the chicken or the egg, because we're basically saying that this can be modeled by a stick at a pivot that's going to be rotating in a circle, or at least a semicircle, and as this is rotating, this thing is going to spin at a constant speed, so just an omega, a constant radians per second, and this car is going to be kind of proportional to this. So when this is up here, the car is going to be at its max speed, 15 meters per second. It's not going to have to, it's going to stay at a constant speed, from here to here. This thing is going to be, if this angle is changing at a constant speed, the speed through here is going to be very linear. But then when we get to here, so you can just see that, it's like, hell yeah. But then here, hey, so look at this. We're going to go like maybe 45 degrees, maybe just 30 degrees. So we're going to go from a 60 degree angle to there to a 60. And now we're going to go 60 to 45. Well, I didn't travel as far. I just went from linear distance. I went from there to there, where from here I went from there to there. That linear distance is farther from 0 to 60, or I guess 90 to 60, than from 60 to 45. This linear distance is going to be a little shorter. And then especially once you get to 45, from here to 30, my linear distance was hardly any. And then from 30 to 0, well, yeah, it's even less. And so that's kind of shows that when a car gets up to speed, it's not moving, it's moving slowly, and then you basically get up to that max speed. Alright, hell yeah, let's tackle this a couple different ways, because this is kind of fascinating to me. What I said was from 60 degrees to 60 degrees, that should be on average speed of 15 miles per hour. So let's just say that, So let's, what I always like to do, if this is a 90 degree, I always like to draw and just kind of try to split this up into thirds. And then that can give you kind of an idea of what 60 degrees is. Maybe this is 30. There you go. And we'll do the same thing over here. So if you just kind of have you're just trying to split this up into thirds. I think that's kind of the easiest thing to do to a 90 degree angle. Okay, that's going to be pretty useful. Now, what do I have here? I have like a 4-inch. So we're going to go out here to 4 inches, and then out here to 4 inches. And I guess it's not 4 inches. What did we say this whole thing is 58. So we have 58 divided by 2, so we have a radius of 29 meters. And this is 29 meters. Now, I swear, like working in radiuses, I don't know, sometimes it's good to work in diameters. Just know that the circumference is pi d. I mean, I think that's going to be the easiest equation to memorize, but I mean, I guess we should all know that the diameter is just 2 times the radius. Sometimes it'd be better to write it like this, pi 2r. But hell yeah, circumference is 2 pi r. And what is the circumference? We're going to have 2 pi times that 29 meters. 2 pi 29. So we have 182 meters. I'm going to store that as the circumference c. And what am I saying? I'm saying that if we sweep out a 30 degrees here and 30 degrees there, for the most part we'll be traveling 15 meters per second through that, swipe. Sweet. And so what we know about, so this 182 meters will be for the full 360 degrees. So you could say a full circle is going to be 182 meters. You could say a half a circle is just half that, so it'd be 91 meters. And then you could say, you could divide it into thirds and say 60 degrees is going to be a third of that. That's going to be 30.3 meters. So is that right? 182 divided by 2 divided by 3. And yeah, so if this is 60 degrees, 360 divided by 60 is going to be 6, so 182 divided by 6. Alright, sweet. So we just did that. But sometimes just to do that, kind of mentally, like, what's the whole circumference? And, I mean, you could use an equation, but I don't know. I just like to do the full circle and then kind of figure out what I'm doing to actually get this arc length. And since we are working in circles, if you're working in radians, like what the hell is a radian? No one knows, but radians times radius is an equation for arc length. And so that's going to be radians times radius is arc length. And then same thing with radians per second. That's omega. That's going to be radians per second times radius. And that's going to be tangential velocity. But you would have to convert this 60 degrees. So if we're going to use this equation, theta r is equal to arc length, we're going to have to take that 30 degrees and say that there's going to be 360 degrees in 2 pi radians, and then multiply by the radius of 29 meters. And that should give us the same answer though. 30 times 2 pi divided by 360 times 29. And, oops, sorry, this has to be a swipe of 60 degrees, so apologize about that. And yet we should get the same answer, 30 point, oh, that was interesting. We didn't get exactly the same answer, oh, because I didn't do this totally accurate. 2 pi times 29 divided by 6, hell yeah. So we get, our arc length is 30.37 meters. Alright, so now where we're at. Oh yeah, so what we just found was that we are going to sweep out this much arc length in how long? Well, no, so we know this arc length is 30.37 meters, and we're going to be traveling at 15 meters per second. Now, it's really good to work with velocity because you can always be like, hey, I need to go 60 miles and I'm going to go 60 miles per hour. What do I do to these two to get like the time, like when am I going to arrive there? That's the question maybe. And so what you would do is you would take, and maybe, I don't know, maybe it's just 30 miles. 30 miles and 60 miles an hour. What do you do to these two to get that 0.5 hours? You know, you can just do that intuitively, but to do that we would take 30 divided by 60. And why would we do that? Well, the units, I like to say the units are the equation. So we have miles divided by miles per hour. Miles cancel and the hours pops upstairs. So this would be in terms of hours. Same thing here. How do we get... so we have meters right here, and then we have 15 meters per second right there. So if we do something to these two, hell yeah, we're going to get a time in seconds. And what's that going to tell us? That's going to be the time to go 30.37 meters. So for sure. So it's going to be the time from here to there. And so that's going to be that time. We're going to get that value. But then what we're trying to find is maybe the time it takes to do a full circle. You know, that might be useful. And this is 60 degrees, and we just said 60 divided by 3, that's 1/6 the circle. So if we find this time and multiply by 6, that's going to be the time for one revolution. You know what I mean? So now we're kind of working towards that. All right, hell yeah. So we're going to have 30.37 meters divided by 15 meters per second. Meters cancel. Second pops upstairs. Alpha D. No, I need to store this. 2 pi 29 divided by 360. I'm going to store that. Whoa. Oh, no, times 60. I'm going to store that as alpha A for the arc length. Or I guess alpha S for that arc length. Use this. So this is going to be... Alright, hell yeah. So alpha S is this term. We're going to divide that by 15. So this is going to be 2 seconds. So right here, I'm going to write that in. 2.02 seconds for this. We're going to multiply by 6. And so for one revolution, it's going to take 12.14 seconds. Okay, hell yeah. So now, and then I was just like, well, what are we actually doing? Well, our problem says like, hey, what's the time to get from here to this, from this stop sign to that stop sign? Well, if we're going to do this constant, if we're going to say our speed is basically a stick pivoted about the center of the, you know, if here's our city street, and we have some sort of, you know, pivoted stick, and it's going to be rotating in a half circle. It's going to rotate at a constant angular speed. That's going to be our linear speed. So when the stick is up here, our car is right there. When the stick is up here, our car is right there. And finally, when the stick gets to here, our car is right there. So the time it takes our car to get from here to there, well, we just figured out that it would be 12 seconds for one revolution, so we just divide that by 2. So I'm going to store that as alpha t. So this is going to take 6 seconds, so the time is 6.07 seconds to get from here to there. Now we can figure out our average speed. Average speed is total distance, so it's going to be distance divided by time. And the total distance is 58 meters divided by that time of 6.07. So we have 58 divided by alpha t. And our average speed is 9.55 meters per second. Hell yeah. Okay, sweet. So, and then there's 2 things that we got here. One, we also know how fast this thing is spinning. And so we had to do one revolution. 1 revolution in 12.14 seconds. We really want to work in radians. What a radian is, yeah, let's draw a circle. So if we have this as our circle, this is our radius. What we want to do is cut a string to this length and then start kind of draping it around the circle. I would get to about there, you know what I mean? And then cut another string and then start drape. I would get about there. And what you're going to find is there's basically about 6 of these strings that you could cut to get all the way around the circle. You're not going to get all the way around because you would need 6.28. You need to cut like a quarter of one of these radiuses. So you'd have 1, 2, 3, 4, 5, 6, and then a quarter of one of the rest. So you get 6.28. That's 2 pi. And that's the definition of a radian. When you drape that first radius up here, that angle is going to be 1 radian. And that's useful. This is useful just by its definition because we can say that radians, we already said it, radians times the radius is the arc length. And that's by definition. Is the arc length. Sorry about the arc length. And isn't that right? Because if we're saying this is 1 radian, and then we're going to multiply it by and then radian is dimensionless. You know, there's no units on it. So we have 1 of those, but then we multiply it by the radius. And so let's say the radius right here is 1 meter. Then our arc length is going to be, that length right there is 1 meter. And by definition, we cut this string to drape around the circle to get up to there, and we're saying that's 1 radian of an angle. So yeah, it's kind of it's very useful because of that. Because then you can be like, oh, okay, if I'm working in radians, I know that just multiply by the radius, and that can give me arc length. And if the angle is small, you know, here's my arc length for a 30-degree triangle, but this height right here is basically the same as the arc length. This arc length S is basically equivalent to, if this is my angle, this is the sine, this is the radius. So this length right there is r sine the angle in radians, and this arc length is just the angle. Theta r. Yeah, sorry about that, or r theta. So you can see that r sine theta is equivalent to r theta. So you can kind of just drop the sine. And just, yeah, anyway. Alright, so let's find the radians. So the angular speed in radians per second. So there's going to be 2 pi radians in a circle. So we're going to have 2 pi radians. And then we said that's going to take 12.4 seconds. 12.14 seconds. So we have 2 pi divided by 2 alpha t. Alright, so our speed is going to be 0.517 radians per second. Alright, sweet. So now what do we do with that? You know what I mean? Like, who cares? Alright, this is the other thing that we can double check, because what we're going to have, if we said this was an average speed of 15 meters per second across that arc length, that's not going to be our max speed. I wanted our max speed to be 15, but we had to kind of come up with an average of what that's going to be. But now that we have the radians per second, this is going to determine our max speed, because we said that radians times radius is going to be our tangential velocity. And the tangential velocity right here at this point is going to be synonymous with our speed, because right here the tangential velocity is purely, you know, going in the direction we want to go. This circle, the tangential velocity right here, well, all of it's in this direction of this spinning thing. None of it's going to be velocity of the car. So that's going to be indicative of the car is stopped. So let's do this. Let's store this as alpha w. Whoops. So this 0.517, I'm going to store that as alpha w for radians. 29 meters stored as alpha r. So we have alpha. So we have W times R is 15. Okay, so that does work. Okay, so we were, yeah, I didn't, okay, yeah. Yep, that does work. But that means that our max speed is 15 right here. It does not mean that our speed is 15 meters per second right there. You know, if we're driving in a car, we're going to reach a max speed of 15 and then go back to 0. So, okay, so that did work out kind of nice. Alright, hell yeah. So now what I want to do is use trigonometry to get a position on this car. And then we're going to differentiate and get a velocity. You know what I mean? And that's it. That's kind of what we're going to finish with. But the interesting thing is that, our distance is related to the cosine of this angle. So if this angle is up here, this is our distance over here. And I want our distance to start off as x equals 0. So I'm going to say like this is 0, but then this is the positive x direction. So to do that, and if we throw in cosine of 0, we're going to get 29. I mean, cosine of 0 is 1, and if our hypotenuse is 29 meters, this distance is going to be 29 cosine of the angle. So to start out, it's going to be 29 cosine of 0, and we're going to have, you know, it's basically saying like this is the origin, and so, but we want to make this the origin right here. And so how we do that is we say this is going to be 29 cosine, so that's going to give us 29 meters, but I need to subtract 29 meters to get 0. So cool. So I think that will work out. So we're going to say our distance as a function of the angle is going to be, now what do I need to subtract? But then if we're right here, this might be like 28. All right, these are always for whatever reason, I always like, you know, whenever you're dealing with cosine, you usually have to like say, I don't know what you have to say. Oh, we're trying to find this distance. All right, hell yeah. Man, I'm so tired right now, but we're going to do it. So, hell yeah. So, yeah, you want to find this distance, you know. So, when this distance is something, that's going to be your distance. And so, yeah, right off the bat, is going to be, okay, so this distance is going to be 29 minus this 29 cosine theta. So, hell yeah. So, that's that distance. So, we can say that x is going to be 29 minus 29 cosine theta. And then so when cosine is 90, this is going to be 0. So then our distance is going to be 29. But then how do we get more distance? Well, when you do cosine of, let's say, 90 plus 30, that's going to be 120. This is going to be a negative term. So we're going to have, and it's, you know, so let's just do that. So we have cosine of 120. It's negative a half. So then, and then the other thing that I guess I was just kind of spacing out. I was like, hey, if I honestly visually don't have this drawn right, because if we sweep out this 30 degrees right here, this takes us to halfway. So if this is halfway, that 30 degrees should be right up there. And so I just don't have this kind of drawn to scale. So that is kind of the, so in a third, so if we divvy up this to be 90 degrees, in this last third, the distance, we're basically traveling halfway. So And we're traveling halfway at that 15 meters per second. So and for this first 30 degrees, we're basically not traveling any at all. You know, so well, I mean, we are traveling a little bit. So you travel a little bit and then get up to halfway, and then this rest of the way you're kind of full speed going the other. Yep. Holy hell! All right, so we have an equation for this distance, and it's going to be this equation, and so and all this isn't a function of time. It's just a function of the angle. So this is just using pure trigonometry. That says if this angle is 30 degrees, my so cosine of 30 is going to be like 0.866, 86.6%, so it's 29. You know, and this would be like, hey, 1 minus 0.866 is 0.13 whatever, so it's about 13%. So at 30 degrees, we're only going 13% of this 29 meters. So that's kind of what cosines and sines are. They're percentages of this hypotenuse. But in this case, we're taking the full length and then minusing this. And so when we say 30 degrees, cosine of 30 is a ratio of 0.866, which is 86.6% of this 29. But we don't want this length, we want this length. So we're not taking that 86.6%, we're basically taking that 13%. That's what we want right there. And 13.13 times 29. So sweet, we went in that first, if it takes 3 periods of time to get halfway, in that first period of time, we only travel about 4 meters. And then in the second period, 29 divided by 2 minus, then we travel about 11. So we travel 4, 11, and then 29, and then that last 14.5. So in this time interval, and then this third time interval, we're traveling half that 29. All right, sweet. So there's our equation. And so what we're going to do now is, since we have this equation, we can use our rules of differentiation. So we can differentiate with respect to time, and that says that the derivative of x, that distance x, with respect to time, and the definition of velocity. Velocity is just change in position, change in time. So this value just becomes my velocity. And then we're going to differentiate this equation, 29 minus 29 cosine theta, as a function of time. But you can see that we don't have a time value in here. I see theta, I don't see time. So what we need to do is use the chain rule that says the derivative, you're going to take the derivative of whatever with respect to theta, d theta, d time. And then so these can cancel, and then you're just right back to taking the derivative of whatever with respect to time. So it looks like this, the derivative of 29 minus 29 cosine theta with respect to theta, and then d theta dt. And then d theta dt is just the definition of omega. So we have the definition, so velocity is going to be the derivative of this times omega. And we already found what omega is. It's a constant, and so that's going to be pretty sweet. And so now we just need to use our rules of differentiation, which says that if we're differentiating cosine, and so the two graphs that you need to know, here's sine, goes up at a 45-degree angle, and then cosine goes this way. Starts at 1 and then goes back down to 0. The slope here of sine graph is, the slope is 1 at 0. So right at 0, sine of 0, the slope is 1. And so what equation when you throw in 0, cosine 0 is 1. So the derivative of sine is cosine. Here, at cosine, here's the graph of cosine. At cosine 0, our slope is 0. Cosine of 0, our slope is 0. And so what when we throw in 0 gives us 0? Well, sine of 0 is 0. So yeah, that derivative of cosine is going to be sine. But this also is a negative sloping graph. So this has to be negative. So the derivative of cosine is negative sine. Those are the two pictures that I draw. And so we're going to take the derivative of this. Now we do have a constant, so that just goes away. And then we're going to have, so the derivative of cosine is negative sine. So we're going to have negative sine theta. We also have a negative here. So those are going to cancel. We're going to have 29 sine theta. So this is going to be our, well, that was just this part. We just differentiated with respect to theta, and now we need to multiply by omega. So this is our equation for velocity. The velocity at any point is going to be 29 sine theta times omega. Let's try it out, because didn't we say our velocity was going to be pretty close to 15 meters per second when theta is equal to 60? And so let's try that out. Now this has to be, well, this part doesn't have to be in radians. You don't have to use your calculator in radians, because this is always just a percentage. Anytime you're working with sines and cosines, they're just percentages. So I can still stay in degrees. So I'm going to do 29 sine of 60. That's going to be 60 degrees to there. Times omega, which is W. And so, cool. And so what this says is 29 meters divided by omega, which is dimensionless, per second. It's radians per second, and radians is dimensionless. So my units are meters per second. So we have a check on units. And what do we have here? And so we're going to have 13 meters per second. So we're not going to have a speed right here of 15 meters per second, because have a component kind of up. We're still getting up to speed. Now in this problem, we never actually reach a constant speed, like only for a very split set. We get up to 15 and then start to reduce. But because this is flat up here, this little chunk right here is going to be the portion where we're actually going to have fairly constant speed. Alright, hell yeah. So now let's, instead of just trusting this equation, let's go back to, what did we say our distance was going to be at theta is equal to 30? We said we were going to use this equation. So we had 29 minus 29 cosine of 30. And we said we were going to have a distance of 3.885. And the time for this whole thing is going to be, that's alpha t. So alpha t is going to be 6.07. We're going to split this up into 3 chunks. So our distance, we're going to travel this distance in, so that distance divided by alpha t divided by 1, 2, 3, 4, 5, 6 divided by 6. So our speed right here is going to be 3.838 meters per second. And now we're going to go back to our this equation just to see if it jives. So we're going to go 29 sine of 30 times omega. And our speed is 7.5. So, so this is kind of cool. I'm glad I did this. Because yes, our speed right here is going to be 7.5 meters per second. But didn't we just say our speed right here is going to be 3.8? No, that's average speed. Because right here, we have 0 velocity. And then right here, we have to have double our average speed. Because we went from zero speed in this direction to actually, some speed in this direction. But we know we actually traveled this distance of 3.83, whatever that distance was, 3.8, basically 4 meters. We traveled 4 meters in about a second. But our car started from a zero speed. We had no speed going in that direction. So that kind of just shows you how from a average speed, the average between 0 and 7.5 is that 3.8 meters in that 1 second, basically. Alright, hell yeah. So that's kind of a little check on that. Alright, and hell yeah. And I guess the last thing that I wanted to show is if here's our two equations. One is a cosine and the other is a sine, and they should be wave equations, and they should be offset. Like I think, you know what I mean? So let's do 29 minus 29 cosine x, and then we're going to do 29 sine of x, and we are going to be in radians. So then the angle, our x value is going to be so like 2 pi. Like here we're going to have pi. This is going to be, so this is going to be, so our window is going to be from 0 to 3.14. So 0 to pi, that's going to be that. And our y is going to go from 0 to 29. So let's just kind of graph that and see what we have. Alright, let's zoom out. Okay, there you go. Now they are, yeah, so, I need to play around with, sines and cosine graphs, or if I do get an equation, might as well graph them just to kind of see. And so our window, so let's go back to our window. We're going to have 0 to pi, and then we're going to graph that. So here, so that's kind of what we have. It's half, and if we go to 2 pi, if we go, yeah, so let's do that. Window 2 pi. So now we have a full cycle. So we're stopped, getting up to speed, coming back to a stop, and then going to another block. So because this thing is spinning in a circle, that's the other thing, is that what I thought a good representation of this is if you start at a stop sign, get up to speed, and then come to a stop sign and stop, and then throw it in reverse, and then go back down the street in reverse, get up to that same speed, and then come to a stop, and then just keep doing that. So you're going to go forward, come to the stop sign, put it in reverse, go backwards hella fast, and then come to a stop. So that's basically what this position is. You're going to go from here all the way as far, this is the farthest you're going to be away at 29 meters, and then on the return journey in reverse, you're going to come back. And your velocity is going to be fastest at the middle, kind of the halfway point, and then you come to a stop at that stop sign, and then when you go in reverse, you're going to have negative velocity. And so one thing that we could do is throw an absolute value on that, and then so all we have to do is square this, and then take the square root of it. It's kind of a cool way to do absolute value. So we're just going to take it to the 0.5. All right, hell yeah. So now this is going to be show you. And how could we actually get that second graph to be additive? So instead of getting to here, that would be kind of interesting. I'm going to spend... Alright, hell yeah. So we're about done. We're about ready to close it up. But what I did do is a second how to go from here to here and then just keep going to another street. And so that's going to be this graph. It's going to be that same distance, 29 minus 29 cosine of the angle, so that we're going to add. But now we're going to try to add it to this point over here. So we're going to have to shift that graph pi x plus pi, because if this started at 0 and then got to here, if we're going to do that same graph, then we have to start our position at pi. So that's going to be that. Now that's just going to be a part of it. And so now this is shifted a full 180 degrees. And but now we need to get that point up there. And so we're going to add that 58 meters. Because once we get to this point, we're already at 58 meters, and then we're going to start this process over again, and then we want to go this distance. So we want to go 29 minus, so the equation for this was 29 minus, where the hell is it? 29 minus 29 cosine theta. But we're starting this plus 58. And then also our angle, though, is starting at, is shifted as well. Shifted a full pi forward. So if we do that, then what we're trying to do is add on to this graph. So hell yeah. So now we do that, and then we can get our y, we can go up to, I don't know, 120. Yeah, so we have 58, and then we're going to, so in another, so this shows from one stop sign to the next, we're going to go 58 meters. And then from this stop sign to the next stop sign, we're going to go another 58 meters. And then so I'm just going to plot 58 times 2, and then that's that right there. And then 58 meters is that point right there. So there you go. And then if we wanted to plot, yeah, so we can't get an equation. So this is the distance at each of the stop signs as a function of the angle. I guess one more thing is how do you get this as a function of time? You basically say that the angle is radians. And what we know is the angular speed in radians per second. So what would we do to radians per second to get radians? Well, you multiply by time in seconds. Seconds will cancel, and then you'll get radians. So this angle radians is omega t. That's going to be radians per second times seconds is radians. And so, so the equation for position as a function of time is 29 minus 29 cosine omega t. And then the velocity as a function of time is 29 sine omega t times omega, which you'd put the omega out here, but whatever. So there you go. Those are the two equations. And I don't know, it's linear motion. So that was the question. How do you get linear motion? How do you describe linear motion as in forms of trigonometry and wave functions? And so, but yeah, let's do this. Let's do, what's 58 times 3? 58 times 3 is 100, so we're going to go up to 180. And then we're going to do another one of these. So we're going to do, so at 58, we're at 58 times 2 is 116. So we're going to have 29 minus 29 cosine of x plus 2 pi, which you at that point 2 pi you don't even need to do that, so we can just just do x, and then plus 1. What did we say? Well, 58 times 2. There you go. And so when we do this one, and then we're also going to do 164. Oh, I'm really tired right now. 174. And I think we're good. I don't know if it likes these multiplication. I'm sure it'd do multiplication. Yeah, of course it does multiplication. Okay, sweet. Cool. Let's graph all that. Oh, whoa, 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 whoa. And then we have to go out in this direction. We have to go to another, so we're going to do, this was pi, or 3 pi, so we just need to go to 3 pi. Alright, sweet. Alright, so this is 1 stop sign, 2 stop sign, 3 stop signs. This is the second stop sign distance, and then this should be the 3rd stop sign distance. Hell yeah! So our graph is a function of position is this blue to black to yellow, and so that's increasing. That's still a wave, you know what I mean? I'm sure you could actually figure out how to draw this graph, you know, just on a 45. You know what I mean? If that's the angle that it is, it's just a sine wave. I mean, it's some sort of wave just in that direction. I just don't know how to graph that. Anyway, but we did it. The red is the stop signs. The blue to black to yellow is the distance. And then the velocity. I guess we... oh, and then... no, the red is the velocity. Yeah, the red is the sign. The red is the velocity. So this is our velocity, 0 to 15, back to 0 to 15, back to 0. And our position is what I just said. Alright, I'm done. Holy hell. So this wasn't a very good one, but at least I did it. And I just, you know, I think it's actually way harder to just, hey, do you have your own question that you solve for yourself? Because there is no answers. You know what I mean? So you're just like, what the hell are we trying to solve? And you kind of just solve for anything you want to. And then, yeah, so there you go. That was pretty decent. Not very good. But thanks for joining me on this, and that's the video.